For hundreds of years, machines have been made to carry us around, do useful jobs, and generally add power to mankind's elbow. Modern engineering, design, and manufacturing now make it possible to increase the scope and the power of these machines dramatically. But of course, it's no use having bigger and more powerful machines if they run amok. And machines have to be controlled with increasing precision to perform the new tasks that may be demanded of them. We shall be talking about how these machines are controlled in this lecture, and you will see examples taken from the world of machines and also from other walks of life. In fact, we'll start with a very familiar kind of control that you've all seen thousands of times, traffic lights. And if I switch on the traffic lights that tell me about starting and stopping, then they go in a cycle, which I'm sure you'll know: green, amber, red, red and amber, and green. And the cycle, of course, is intended to prevent a free-for-all taking place in the middle. Now, usually that program is preset and stays fixed forever. But there are some traffic lights in which the cycle is controlled by a computer which is fed with information about traffic flows. That would take us a little too far afield at present, but we'll come back to that idea later. A few hundred years ago, automatic toys were all the rage in Europe, and some very elaborate specimens were made up, usually worked by clockwork. Here I have an example made by Frank Nelson in the north, the simple enough model, but it illustrates the kind of thing. Usually these toys were wound up and then released, and then they did their antics, and that was the end of the cycle. But here I have to turn the handle, and if you observe carefully as I reach over and turn the handle, you see the lion tamer is persuading the lion, but the lion is unconvinced, perhaps a little more firmly the next time round. And the lion acknowledges the message, and finally, hey presto, the unexpected happens, and the lion gets bitten by the lion tamer. Some very elaborate versions of this were made, mechanical mechanisms of great complication, and the fine art in their craftsmanship. And we have yet another example to show you of a program device. The programs are set beforehand, of course, traffic lights, a little mechanism inside driving the lion tamer. And here we have a marvelous example of this splendid machine. At the threshold of 1984, we can listen to the tones of a more leisured and perhaps melodious age. I'm sure you'll recognize the tune. And of course, the software in this case, to use a computer term, consists of those discs that have little spikes sticking out underneath them. And they drive a set of vibrating reeds underneath which produce these beautiful harmonious tones. These devices were, in fact, the forerunners of numerical control, which is now widely used and which has led a revolution in manufacturing. And we'll return to that later in the lecture. So far, we've looked at fixed programs, things which are set beforehand and then repeat themselves time after time. Let's have a look at, at another kind of control system in which we can make perhaps some variations. It's set up on the table. And let me tell you first what it consists of. There's an electric motor on this little platform which drives the disc. And that's all. The idea is, let us suppose, that we would like to drive the disc at a constant speed. Maybe a set of different speeds at different times, but at a given time a constant speed. And to help me with this operation, I would like to invite a volunteer to come up, and we'll get the machine going, and we'll see how he's coming on. Perhaps you can have the young man at the end there. And I'll tell you what to do, and then you can see how it goes. Now, to control the speed of the motor, there's a little rheostat or variable resistance here, which will control the voltage going into the motor, and that we hope will control the speed. So if we now turn the machine on, it should be all set to go. It's just ticking over. We can see the speed registered on the big meter, and I would like now to ask you if you would set it for about 50 revolutions per minute. If you come just to the side there and move the handle to about the green position, and look at the meter, then settle it down when it comes up to about too high, down a little bit, about 50, and that would be the setting for that particular speed, 50 turns every minute. Now let's try for 100. Could you just bring it towards you a little and get on to 100? That's very good. Now stop. You've overshot the mark slightly, but it's in that region. And one more time up to 150. Away you go. And just stop it before you get there. That's fine. Just in 150. Everything there is fine. He's got the speed settings. He could mark them on the controller. And provided nothing changed, then the speed of the motor should run out at that chosen speed every time. But suppose something changed. Suppose the load changed. What would happen then? Could I have another volunteer? Would you like to come out? And you can be the load, and he's going to be the controller. And he's going to try and keep the speed, say, at 100. Take it back to 100 while I explain what's happening on the load. For the load, you can apply a brake by moving that weight out, and this puts a little brake on the wheel and will, of course, slow it down. So we'll start off without any load, and if you take the weight back and put some load on, it's your job to keep the thing at 100 revolutions per minute. Now I'll come around here and we'll just work this together. Pull it out quickly. Okay. Now he's too low. Straight back when he goes back. Push it right back. The other way. And can you follow what he's doing? Okay, out again. Now back. Well, you can see what's happening. Thank you very much. That's very well done. You see, what they've been doing is using a form of feedback, and the young man on that side was adjusting the load, and his colleague on the other side adjusting the voltage control to try and keep the speed constant, which may be important for certain applications. And we can illustrate the difference between the two kinds of controls that we've been using by some pictures which will make the point. In the first instance, there was no feedback at all. We just set the controls and away the machine went, and the speed was determined by all the other factors that were involved. So that is described as an open loop control. The voltage goes in at this side through the controller to the motor, and the speed of the output may or may not stay fixed. If the load changes, it won't, as we've seen. But we improved that greatly in the next picture by putting in a feedback element, and the controller was actually observing the speed as the speed changed and was adjusting the voltage to compensate for the changes in the disturbance or the load. And that way round, a much more effective control system is set up, and that application of sensitive feedback control lies at the basis of many modern control applications. It's quite simple, and we can illustrate some of the applications of this in a minute. But before we do that, let me just explain that we can, in fact, describe quite complicated systems this way round. If we have an engine here, for example, which may be a rather complicated machine, we can describe it with a mathematical expression inside, which tells us how that output depends on the input. That mathematical function has a special name, which I will tell you, which is called transfer function. And by use of that, and by breaking down very large systems into bits, into little blocks like that, the control engineer can set up a description of a very complicated system and deal with it piece by piece, and also discover how the whole system works in a mathematical way. Now, I can illustrate that and the differences that may arise in different sorts of systems very simply. Here we have a rather stiff steel lever, and suppose the simplest of operations, this is the input at that side, and that is the output. Well, as you can see, if the lever doesn't bend, the movement at that side is proportional to the movement of this side. And in that case, the transfer function, so to speak, is simply the constant of the lever. But if we have something which is a little more complicated, and here I have a rather flexible lever, as you can see, then the result is not quite the same. If I put the input in, bang, then the output just doesn't move and stay there, but it oscillates about the position that it finally comes to rest at. That's because of the flexibility in the part. And in fact, we can put inside the little blocks, the transfer functions, an allowance for the flexibility of the part. And indeed, in many applications, it's quite essential to do that. Let's look now at one or two other kinds of control systems, for which I'll need some agile volunteers. And we shall see how they make out. These are not all engineering applications, but I think you'll detect the kind of feedback mechanism that may be involved. So can I have perhaps one volunteer? How about that young man there? Would you like to come down? Your name is?
Guy.
Guy, okay, Guy. Now, we're going to investigate Guy's stability. If you'd like to stand there, and you're extremely stable, you're standing very still, which is excellent for a start. Now, what shall we do? Would you like to put your hands behind your back and stand on one leg? Put your knee right up, don't be afraid. That's pretty good. You can see he's adjusting rather carefully from side to side, but he's staying upright. Now, would you like to rest your leg? Just get your muscles back from it. That's right, okay. And now do the same thing with your eyes shut. Very much more difficult, as you can see. Thank you very much. That's not a bad shot at all. Guy had at least two feedback circuits going. One was the internal sense of balance in the stance that he took up. And the other one, of course, was vision. And he was able to look at a fixed point, and that helped him to stand on one leg. When that was taken away, then it was very much more difficult. Volunteer number 2. How about the young lady at the end there? Yeah, would you like to come out and try your hand at something? This is, again, a matter of stability, and we'll give you this wooden rod. No tricks, it's nothing, absolutely straightforward. And I'd like you, if you would, to hold that upright on your hand, or if you think you're very good at it, on your finger. So your name is?
Angela.
Angela. So Angela, take that, whichever hand you prefer, and see for how long you can actually hold that upright. Don't be afraid. That's very good. That's not bad at all. Not an easy task, and what she was doing, of course, was moving the hand to compensate for the motion of the rod, and she had freedom to move this way, that way, or up and down. Try it yourself sometime. Now, just to show that things are not always what they may seem, if I put a weight on the end of the rod, do you think that'll be easier or worse?
Worse.
Worse, okay. Well, use the same hand, if you don't mind, and try it again and see how you get on. Now, is that easier or worse?
A lot easier.
It's much easier. A little surprising that, perhaps. Thank you very much. You did very well. It was, in fact, much easier the second time, because although this weight at the end you would think would cause it to topple faster, in fact, it causes it to topple more slowly, because the moment of inertia of the whole thing, for those who like moments of inertia, is that much larger, and so the acceleration sideways turns out to be less. So, two examples, not engineering, but there are some resemblances. If you think of the shots of rocket takeoffs that you've seen, things going to the moon and so on, there the controller has to provide for a very accurate positioning of the rocket as it takes off. And although the mechanism isn't the same, of course, some of the mechanics is at least similar. Now, something going a bit towards an engineering control system. This is a car which can be controlled, a model car, and it's to be switched on. And I will now switch it on. And you will see that when I clap my hands, it picks up a signal from the clap and will in fact change its ways. And I'll do that once or twice. Then I'd like to invite you, if you think you can all clap together, which I greatly doubt, to see if we can orchestrate ourselves in a way which doesn't confuse the car unnecessarily. Now let's hope it will actually start. It starts. Stop. And that's remote control. You were excellent. You were practically, there was one person up there to start, I think, but otherwise it was extremely good. So that's a remote control by acoustics, if you like. But now we get a little more sophisticated, and we try a slightly temperamental experiment with a model car known as Wild Willie, for which I will need the volunteer, and we'll have one who's had a little rehearsal, I have to admit this, in the person of young Timothy. Now, what we shall ask you to do, Timothy, is to control the car and to drive it actually between two gateposts. Do you think that's wide enough? We won't make it too easy for you because we'll put it off at an angle for you to begin. And may I explain that the controller, hang on for a minute, that the controller that Timothy is using so skillfully will do two things, and it'll do it by a radio transmission, do both. One is to drive forward or backward, and for that he has the controller on this hand. And the other one is to steer to right or to left, and for that he's got a separate controller on the other hand. And many of you, I expect, have have worked these machines or something similar. This one goes rather fast. So would you like to drive it through the two gateposts? That's very good. Now, could you be very clever and bring it back again? Oh, very good. That's excellent. Now, we're not actually going to let Timothy off the hook. He's obviously very skilled at this. And we want him now to take on the different role, that of a NASA controller who's driving the Jeep called Wild Willie on the surface of the moon. Let's think about that a minute. The controller sitting in Houston will be transmitting signals to the moon, and they will take a finite time before they get there. So there's a separation between the action and the result. The time of transmission is a little over a second. we can't reproduce that. But then on the reverse the transmission, i.e. when the television cameras on the moon take the picture and transmit this back to Timothy, then there's another second and a bit delay in the signal before it gets back to the Earth. In other words, the controller is working in total with about 2 2/3 seconds delay. And that makes it very, very difficult indeed to control anything, especially a wild willy car like this. But we can't do both. We're doing one, though, and if you'd come with me, Timothy, we shall start you off. Shall we start off in this position, or yes, we'll start off in that position and give you a better chance by opening those perhaps a little wider, because this is very tricky indeed. And we'll take Timothy round to a special monitor. You will now see on the screen 2 pictures in a moment, of which Timothy can see but one. What he can see is the picture you see in the top right-hand corner of the screen. And that picture, with great ingenuity indeed, the BBC engineers have contrived to show a simulated delay. And that delay is about a second and a bit. And that's the only part that Timothy can see, poor chap. We, on the other hand, including me, we can see the entire field of view in real time. We can see what's actually happening when it happens. Timothy can't. He can see the picture with a simulated delay. Now his task is very difficult, and we'll see how he makes out. So would you like to start the process going? You can see the Jeep there, can you? In the background? Okay. I hope you can see both pictures there, which in the delay, the series of stills appear, and the delay has been introduced into the stills. But Timothy is working only with that. My turn, I think. It's getting crucial now. You're on track, left. Okay, straight forward, I think. The other way. Close. Good. Good. Right through. Fine, that it's well through by now. I expect it into the real world. That's excellent. Thank you very much, Timothy. Timothy, as you saw, was adopting an excellent technique for the purpose. He was doing it in pulses, and very cleverly waiting to see what happened after the pulse he'd injected had taken effect, so that in a sense he was compensating for the delay that way. If he had a continuous picture going with a delay, I rather think it would be a little more difficult. Now, during the Second World War, control engineering took a major step forward as necessity became the mother of invention. And it was important to be able to move large objects rapidly and precisely, like radar antennae, for example, or heavy gun barrels, without putting a lot of physical effort into turning the great handles that might otherwise be required. And so there was born a class of control called servo mechanism, which by putting in a small signal at one end could produce a large motion of a large object at the other end, the muscle being provided by the engine or the electric motor that actually did the driving. And we can reset our little machine that we used beforehand for the speed control. We take the rheostat away entirely and now work with another volunteer, which I'll ask for in a moment. But first let me explain the various parts. Think of this as being the radar antenna at the end, a very big thing that has to be driven around precisely. And think of this as being the controller. I'll just thread through, I think, here. It comes out that way, that's all right. And for this now, the action goes as follows, that when this handle is turned, that's the control, very light touch. A signal is sent, an electrical voltage, into the system, and it goes into this point, which also receives a signal from the output, that's this end, proportional to the displacement there. The difference between the two, that's the feedback, is the error. And that error is magnified several fold in the amplifier. That goes to the motor, which drives this. So the whole system operates on an error basis, the difference between the output and the input at this end. And such controls can be made very accurate and very precise and also very powerful. So now with that little story, could we have the volunteer up, and I'll just make one or two adjustments to the controls, and we'll switch it on, and then we should be in business. So could we have a volunteer, perhaps from over that side? What about the young man there? Your name is?
Sean.
Sean. So we'd like Sean, I think, to stand over here. He has to stand fairly close so that the result can be seen by everybody as he does it. If you turn around a little bit and get behind this thing, and just step over there, that's it, and hold it in your hands, and be prepared to move that control stick when I say so. Then, if you can see, as I hope you can, the output shaft, that's the big heavy machine part that's to be turned. We can see what happens when he turns it through, say, one of those divisions, or keep turning rather slowly until I say stop. Stop. So the output, in fact, follows quite closely the input that Sean is putting in. Now, suppose he were to put a sudden movement in, then we might see something interesting. If you move it back, say, about a quarter of a turn very quickly, just knock it back, and it goes back again, but it overshoots the mark and oscillates a little bit before it comes to rest. And that's a characteristic, rather like the lever, but with a different mechanism, of the overshoot and the oscillation that you can get with a servo mechanism of this kind. Would you like to move it sharply a quarter down and then sharply a quarter back just to convince us all? That's fine. And it shakes about, which is not very good because you want to get the thing dead beat. So if I turn up the amplifier gain, that means more voltage into the motor. Let's try it again and see if that's improved things. That's made things rather worse, I think. Could you just do another quick turn? It's definitely worse, yeah. So let's make a simple adjustment now to the control box and turn up another little knob which affects the current in a certain way. It's equivalent to putting damping into the system. This is called velocity feedback. And now if you turn it a quarter of a turn quickly, then it's almost dead beat, and it will almost sit down there happily and come back a quarter of a turn. And there you are, it's settled down to a nice, stable position. Fine, thank you very much, Sean. A very common way of testing systems of this kind, and of many other control systems as well, is putting in not just a step like that, but an oscillation. And then it turns out that if you can relate the output and the input well, you can find out, if you didn't know beforehand, what's actually inside the system. And in some systems are so complicated that it's not fully understood how they behave until the test of this kind is conducted. So here we have an oscillator that I can turn on, and now will. And that's putting an oscillation into the output electrically. It's as though someone were turning the lever, but we do it with the electrics because that's more controllable. And I can change the frequency and the amplitude. I'll set a certain amplitude which is like that. Now turn the frequency up so that the shaking electrically is getting faster all the time. And you can see that responds quite a large motion. Perhaps even larger. The frequency is going up all the time. And now it's at very high frequency and the oscillation is very little. In fact, it's passed through a state in which the oscillation might become dangerously large, condition of resonance, if you like. And if I bring the frequency down again, it'll pass through that. Now I'm coming down to very slow rates. And now it's stopped. That kind of frequency testing is common practice and is used very widely. So there we have something about servo mechanisms and the way that they've developed. So let's turn now from one machine, the machine you'll be looking at, to a very large control system indeed. And this is the electricity supply to England and Wales. It's probably the largest single electricity supply system in the world. And it's got to provide for variations in demand that may be very considerable. So I'd like to show you a slide of a very special day, some 2 years ago, in which the demand fluctuated very rapidly indeed throughout the day. So if we can have the first slide up. This was a famous day, and if I come over here, I can show you what it's all about. First of all, to compare what happened on that day with an ordinary day about the same time of the year, look at that dotted line, August Bank Holiday, 25th of August 1980. And that's how the demand of electricity went during the course of the day. People got the lunchtime the meal being cooked at about 12 o'clock, a big demand for electricity there, and rising up again towards dinner time. But on the day in question, look what a change there was. As the royal wedding progressed through the day, during the course of the service, there was a very sharp drop indeed in total national electricity demand. Everyone had turned all the cookers off, washing machines, ironing, and so on, and they were sitting down watching watching the wedding. And then you can even detect, and this is very interesting, little peaks of renewed demand during the course of the service, and then as the service was completed, then the demand was restored about to an average performance. So that was rather an exceptional day. But then there are big variations in an ordinary day as well, and big variations between summer and winter. So how do they do it? Well, the next slide shows you the center of operations of the Central Electricity Generating Board. And these men have the responsibility of deciding what power to call up from 6 areas in the country with about 100 power stations at their disposal, and the total of about 350 turbine generator sets providing the electricity for the whole country. They have to estimate the requirement the day before. They do it on a daily basis. Some extraordinary variations, like, for example, 1 degree difference in centigrade in the temperature means a difference of about 600 million watts in the national demand. And then also cloud, wind, and other things come into it. So the estimators have to be very skilled to get it approximately right. They'll never get it absolutely right. And then they can tune the system by giving directions to various area controllers from this place to either shut down or start up new machines. About 50 machines are usually available for variations of this kind. This is a map of the country with rather like the London Underground, except it's put on the side, and that's the north and that's the south. And you see various other maps here. If we have the next slide, we can see a little more detail. Well, that shows the areas, and it also shows the amount of electricity in megawatts transmitted or exported from one area to the next. At this particular time, which I think was at a very unusual time, early on a Sunday morning, the northern area was exporting to the northwest, but was receiving power from the southern areas. So there was an electricity flow up that side of the country and across and into that area. Usually, though, the flow is the other way, and the electricity flow is more downwards than upwards, so to speak. But that shows the export-import situation. And 2 little clocks up in the corner are quite interesting. One is the mains clock, and that's run off the mains frequency. The mains frequency is allowed to vary by law only between 49.5 and 50.5 cycles per second. In practice, it's kept to a narrower band than that. And also, there's a limit of the amount of delay of the mains clock against a very accurate crystal clock, which represents, as it were, the true passage of time, And here the mains clock is registering, I think, 15 seconds slow, which is the allowable limit. So that all these controls have to be very carefully handled in a centralized way in order to make everything come out right. That's an example of optimal control. The controllers have to decide on the basis of economics. Economics must come into this. Some power stations are more expensive than others. Where to call up and generate the electricity to keep the price of electricity as low as possible through these operational means. Another example of that kind of control, quite complicated, is that of the petrol engine. And here we have such an animal, a petrol engine. If you've thought about it, motor car engines have to operate under incredibly variable conditions. Cold starts, hot running, high speed, idling, stopping and starting all the time. And so it's not surprising that the engine cannot always operate at the maximum efficiency in terms of burning the fuel. In fact, there can be quite big variations from cylinder to cylinder, and even in the same cylinder from cycle to cycle. So engineers are busy developing ways of improving that by adjusting the amount of petrol going in and the timing in a rather different way. And the next slide illustrates how that is being developed. And it involves petrol injection rather than the carburetor device there. And here are 4 injectors for a 4-cylinder engine into which the petrol is being very carefully metered. And it's metered in the knowledge of the best combustion, the most efficient way of doing it, and a variety of inputs taken from the engine itself, like, for example, the speed, the air temperature, the pressure at the various vane switches, that's the distributor position and so on, coolant temperature, all going into a little calculation. And at the end of the calculation should come out the best amount of petrol to go in for those conditions, the timing of it, and when the spark should be sparked. This is what it looks like in, or part of it anyway, looks like in actual operation. This is the distributor which delivers the spark around to the 4 cylinders. And much of the action takes place inside the cylinder, inside the head of the distributor, which is driven off the engine. Speed measurement, position measurement, and so on. Coming from the other end are the various measures, temperature, and so on. And they go into a little microprocessor, which is some distance away from the hot, noisy engine end in order to optimize performance. So far, the trials have proved promising, and there is no doubt that such controls will develop in this way for improved efficiency of the combustion. An application of control that's made rapid advances in recent times is manufacturing, and shortly we shall be looking at the robot performing its operations. But before that, I'd like to show you a short film, which is not of a robot, but of a big machine tool, which is controlled by a computer. The possibilities there are now being realized in industry very widely, and the film will show you some of these happenings. So if we turn to the film, we first see one of the operators loading the machine, the computer, with instructions. And shortly the machine will be driving away. The operation is that of machining a cylinder block of an engine. You see it's a very large machine tool, and the engine is being presented to the tool, which will shortly engage and start boring the cylinder block. Now it's gone into a different action, and there's a tool change taking place, and we'll shortly see that little tool reaming a hole, again in the cylinder block. Notice how the engine itself is being positioned, the workpiece is being positioned for the action, and there goes that operation. And all this can be preset beforehand, programmed, and the speed of operation can be greatly increased. We can't show you a big machine tool in operation in the lecture theatre, but we can show you something like it, which is a drafting machine which will make drawings on a predetermined program. And here we have that before us. And if we could firstly see the engineering drawing that's to be drawn on the screen, then you can see what it is the drafting machine will actually draw. That's just coming up into focus. And if you watch the plotter, that's the drafting machine down below, in action, you will see it performing in a very spectacular way. Right, so if we can start the action going. Firstly, it's copying the shape of the part to be machined, say, to be made later. And it's doing curves as well as straight lines. Now it's doing the other view. It's a busy little fellow, and shortly it'll change the pen and put in another color. Another nice curve. Now it's snatched another pen up, and it's putting in the hatching. It's changed its mind a bit about the next color, I think, and now it's putting up a center line. And to make a nice, neat job of it, putting in a frame, and shortly it'll tell us what it's been doing. There we are, complete. If you could buy one of these machines, it might save you a lot of trouble in drawing out engineering drawings, and in fact, that's what's happening. And the skills of the draftsman are, in a sense, being transferred to the skills of putting in the computer program and getting this thing to whiz away at high speed and turn out drawings at the rapid rate of production. You've all heard about robots. Well, now we start to talk about robots. The actual word robot was first set out and written about by a Czech writer, Karel Čapek, who used robotnik, or worker, to refer to a machine with human-like qualities. And no doubt you have seen many pictures of robots of a monstrous kind, those that can possess superhuman strength but no heart and no soul, and very dangerous and so on. But they've been written about chiefly to curdle the blood of the readers and have very little place in reality. But perhaps our model will curdle a drop of blood or two, but I guess not much blood will curdle with this little robot. As he slowly waddles across the stage and is in grave danger of falling over, I think, at any minute. So there he goes quite happily. But that's a rather unreal robot, and we would rather think about real robots, on which engineers have been working for 25 years and which have now reached a very advanced state. And these robots, like other machines that engineers design and make, are simply there to do a particular job and to do it more efficiently and perhaps more quickly than otherwise is possible. There are all kinds of engineering robots about. Some do actually trundle about on wheels. A few walk experimentally. Experimental robots, at any rate, walk. They are used in many applications, in the oceans, in space, in nuclear reactors, and in other places where the human life is dangerous or the job is extremely repetitive and tiring. So, in order to illustrate some of these applications, let's look at the real robots, industrial robots, for which I have a short film. So, if we can start with a simple robot sequence that's just picking and placing. And now it's actually working in production and is lifting a part out of a machine, a press, and here it goes again. And now I think we'll see it lifting a very hot piece out, and now a piece that needs to be held and pieces broken off it. Another hot piece going back into a different machine. Now this is very interesting. Here are men in a very unpleasant job painting the undersealing on a car. They work in a pit, they have masks, and altogether it's very unpleasant. Now this man is actually teaching a robot what to do. He's taking it through the actions. The memory in the robot computer is storing up the sequence, and shortly that's the magic eye detecting the model of car and switching in the right program for the robot. Now the robot is faithfully reproducing the actions, and here he goes spraying around and completing the job and removing the people from a rather dangerous environment. And their job now is to control and supervise the robot's operation. Here's the Puma robot of the kind you'll see in action in a moment, doing a very agile piece of work, and it's putting together an electrical circuit, a loom, a number of electrical wires in a certain way for a pickup truck. And it's programmed to select the appropriate wire, to run through the various positions quite rapidly, and that it's doing now. Really quite amazingly agile. And the next short piece of film, I'd better introduce by saying it's a film about experimental robots, and it was taken in Japan, where I worked some while ago. The film is taken over a span of many years. The research had been going on for a long time, and if we start the next film, you'll see some of these research robots on which some development work was being done. Here's one picking up a peg, and it's about to put it in the other hole. Now it's got some sensors in the gripper, and it will feel where the hole is, and then sort itself out, and then push the peg into the hole. Little struggle, but away she goes. The next time round, there's a hammering robot, very enthusiastic one, as you'll see. Bang, bang, bang it goes. So enthusiastic that the head falls off. Now it's feeling to see if it's finished the job, and a few more mighty swipes. And here's somebody trying to fool the robot, which is being using a television camera to position the robot. And here's a robot doing a baseball swing, picking up the ball, and what a good shot. What I'm not sure about is whether they put the bucket there after the robot swung the ball the first time, but anyhow, it got into the bucket that time. So the next bit of film shows some work that some research assistants of mine have been involved in, and we'll have perhaps a quick slide or two beforehand to illustrate the point. The job here was to put some small metal plates, there's one such plate, in position on that bank of tubes. The tubes were part of a nuclear boiler, a boiler for a nuclear power station. And that's a bit of metal. There were millions of these that had to be welded on. And they had to be put in these positions in large numbers throughout the whole installation. The next slide, I think, shows the idea. A television camera was to be used to reflect light off parts of this little spacer, as it's called, and that's the configuration. Camera would pick up the position, and the next slide shows the arrangement that was used. And I think, in fact, we probably now go into the film. So if we could start the film going, that shows the robots which are doing welding without any camera attachment. The tube bank is down on the flat, and away they go. We'll shortly see the experimental setup with the light pointing downwards and the camera attached to the top of that rod. It's viewing the scene, this little spacer, that's what it's looking at. The picture is now being tested by the robot gripper. That's the scene on the display unit from which the calculations are worked out, and that's again the final installation. And the robots are busily back at work. That way, the precision of the operation and the speed can be increased in a very useful way. But now we come to a robot that we can demonstrate for you. It's the Puma, which stands for Programmable Universal Machine for Assembly. In fact, it'll do many other things as well. Mr. Hammond is in complete control, I hope. And so he'll now start the robot off. So that's the starting position. It has several movements. That's waist, now shoulder, as for the right arm. That's a shoulder movement as for the left arm. That's two movements. That's elbow, that makes three. And then we have three movements at the wrist. Roll, pitch, and yaw. So that's a complete set of movements with a gripper at the end. That head can be replaced by various devices according to the job required to do. Now, those are the single movements. There's an electric motor driving each of these joints. Now we'll show you that the arm can be coordinated so that, like your own arm, you move various joints at the same time to produce certain motions. And so let's go off with a coordinated motion in a straight line. Call that the X direction, if you like. There she goes. Now we'll do the Y direction. And the Z direction. And then he can do inclined lines. I'd better let him start, I think, so I know which way he's going for this. All the joints, practically all, are moving as he follows that trace, and now he's doing that one, and no doubt we'll follow it by that one. So that's three lines in different directions. So now he'll show you something about reproducibility, i.e. getting back to the same place in succession. And for that we'll apply a pointer. It's gripped. I will now stand safely back and watch the proceedings. That's a point in space, a marker, and he's approaching from behind. He's now doing a rapid movement in space, showing off a little, you might say, and coming back from the top. Important thing is that it's getting back to the same place. He's showing off again, and now he's coming in again to exactly the same position. That's good. So you can see it repeats itself, and it can do these motions in between. We take the pointer out now and invite a challenger to see if he can beat the robot at a game at which I have to say the robot is extremely good. So do we have a volunteer? Douglas. Douglas has, I have to admit, tried this before. And this is the competition. Douglas will, in a moment, take up this point, this little curved piece of wire, and I switch it on. You can see that every time he touches that wire, it makes a rather unpleasant noise. Now, your job is to take it around, Douglas, if you will, in one hand around the wire and see how far you can get without making funny noises. Once. Doing very well there, keep going. Can you just go a little faster, do you think? 2, 3. That's very good. If we stop at the top, that's a very... and you're putting it back, and we'll switch the machine off. And I may tell you that that's not an easy thing to do. I touched it about 20 times on the first curve, so Douglas has done extremely well. You notice I switched the machine off. Well, we'll start off by getting the robot to switch it back on again. It's on. Oh dear. That's not very good. I think it can do better than that. Mr. Hammond is now telling it to get going. Oh dear. Couldn't you do something to it and get it going round without doing that? Ah. Now he's got it going. So far, so good. That's going to be a clean run, I think, this time. Well, that's very, very good. Can it do any better than that, do you think? What's it showing off at the top? The job is not quite yet done. Like all good robots, it's going to see it to the finish, and now it switched the machine off, I think, or is about to. It is, yes, and now it's done its job. It's going to do a turn or two, I rather think, and well, you see what a versatile machine we have. That brings us to the end of the lecture. You've seen a number of control systems in action, and you've seen this marvelous machine doing its turn. The next lecture will be about fluids and flight, and we'll end in a moment on a very melodious note.